Okay, without further ado, Alastair Harborne.
Well, thanks, Bob, for the invite, and to everybody on the CAC team for putting this event together. Having said that, he did give me this title. So it's not going to be a laugh a minute, I'm afraid. Rising seas, warming oceans, and ecosystem collapse. But I will say two things. One is I'll try and talk about some more positive messages at the end. And I'm also a bit of a setup man for Liv and Erin, who are going to talk to you about what we can actually do to address the threats to tropical marine ecosystems. So I run the Tropical Fish Ecology Lab at FIU. And the other thing I'll say is, just in case you haven't read the bio, I'm from the UK, so you don't spend the next 40 minutes trying to work out whether I'm English, Australian, South African, or whatever. So now you can focus on what I'm saying. All right, so what we're going to do is we're going to think about the threats to climate change, to coral reefs in particular. We touched on that a little bit this morning. What are the impacts on ecosystem services? And by ecosystem services, I mean these things on the left here. So protein provision, so fish, tourism, obviously a major part of Florida's economy, and fishing and all the funds that come from that. And as I say, I'll finish up at the end just talking a little bit about what we can do to address some of these threats that I'm gonna talk about. And so you can't read all of the text, but this is a nice infographic from the WCS that just summarizes some of the benefits of coral reefs. You're probably aware of their biodiversity, fish and corals and invertebrates, and the kind of things that they provide, as I just mentioned. Storm defenses, protein, tourism, nutrient cycling, biodiversity, all that kind of stuff. And then we have the yin to the yang of the benefits of coral reef ecosystems, which are the threats: invasive species, pollution. And we're gonna focus today. Unfortunately, or maybe fortunately, I don't have time to go through all the threats facing coral reefs, so I can focus on this aspect of climate change. And I put this in. I figured at this point in the day we'd probably seen figures like this, and indeed we have. And Bob and Ken spoke eloquently about the changes that we've had in carbon dioxide over the year, and you can see that kind of cycling that they talked about, and then where we kind of sit in a historical context. And of course, where we go from here, this is a little bit out of date, is up to us and some of the things that we're talking about today. So what are the threats to coral reefs from climate change? So here's a healthy stand of elkhorn coral, and it is threatened, and all the associated species are threatened by temperature rise, which you probably have heard about, ocean acidification, which you may not have heard about, and then some aspects of sea level rise. We don't necessarily worry about our marine species being affected by sea level rise. Feels like more sea is a good thing, but I'll show you a couple of examples, or one example of how it might be a problem to some, particularly fish species. So before I get into this, I do need to give you the 101 lesson in corals and what a coral is, for those of you who aren't aware. And I asked the indulgence of my coral biology colleagues for a fish guy talking to you about corals. But here's a reef building coral. So you probably know reefs are made up of corals that grow, and then they die, and then they leave behind the limestone skeleton, and other corals grow on that, and so the reef grows. So this is what you would see if you saw a healthy stand of this coral out there. If you zoom in, what you'll see is that they're made up of all these individual coral polyps, and you can think of a polyp like an upside down jellyfish sat in that limestone skeleton. These polyps are all genetically identical to each other. A single polyp settles on the bottom, metamorphosizes, becomes a coral polyp, and then divides into 2 and 4, 8, 16. My maths is not going to handle any further than that. And eventually it grows. And so you can get some idea of how slowly that must happen. This coral is probably a couple of meters across. Some of these corals are only growing at a few centimeters a year. So it takes a long time. And so just keep that in mind as we talk about some of the things that can affect corals, about how long it's going to take for them to recover. And so here's one of those polyps kind of sliced in half as one of those jellyfish. Let's start with the simple stuff. So corals get some of their energy from catching plankton out of the water. So they have these tentacles, they pull plankton down towards their mouth and then into the stomach. So these are fairly simple organisms. On those tentacles, they have these things, nematocysts, these stinging cells that allow them to catch plankton. We shouldn't be touching corals, but if you do, for most corals, these nematocysts are not strong enough to get through the skin on your finger. We do have places where our skin is thinner. The inside of our nose is one, the tongue is another. So here's my public service announcement for the day. If you ever find yourself with a coral, don't lick it, and certainly don't stick it up your nose. So then you have this limestone skeleton that when the coral dies, it leaves behind that building block of the reef. So my word of the day for you that might help you in a crossword at some point in the future is zooxanthellae. And zooxanthellae are the secret of how corals exist in nutrient-poor tropical waters. The reason why the water is so clear and blue is there's very limited nutrients, or naturally. And so corals have solved this problem by having this symbiotic relationship with zooxanthellae. You can think of them just as they are just algae within their tissues. I'll also apologize. I've been in the US 9 years. I can't bring myself to say algae. I'm going to say algae. You're smart people. You're going to have to translate it in your mind. I'm also going to talk about herbivores, so a heads up, that one's coming. So these are algae, so that they're photosynthesizing. They're generating 80-90% of the coral's energy by passing on those sugars to the coral. It's beneficial to the zooxanthellae. It's beneficial to the coral. So it's this unique or unusual or very effective symbiotic relationship that allows corals to build things that we can see from space, like the Florida coral reef, the Belize barrier reef, and the Great Barrier Reef. The problem is when the water gets too warm, and we're not talking about twice as warm as it should be. Most of these corals are living pretty close to their thermal tolerance. So it might only be a degree or two. They can start bleaching, and some of you may have heard about this process of bleaching. So these corals, the zooxanthellae give them that brownish, greenish tinge. But under high light irradiance, light intensity, and also under high temperature, basically that relationship just spins out of control. It's like a high-performance sports car, and you've just kind of got your foot down on the accelerator and redlining the revs, and eventually the whole relationship begins to break down. And as a stress response, the corals expel those algae out of the tissue, and the coral goes white. That doesn't mean that the coral is dead. It can still, if the water cools down, it can still get some of those zooxanthellae back, get back its color, and continue as it was. It might not reproduce that year, or there might be some other stresses, but it can go on living. Alternatively, if the water stays too warm for too long, obviously in the same way as if I removed 80% of your calories, you would eventually wither away. Corals will do the same. And so these bleaching events can lead to large-scale mortality through this breaking down of this important relationship between corals and their algae. And so when I started first going to coral reef conferences in the early 90s, there wasn't much discussion of things like bleaching. And then the big mass coral bleaching event of 1998 happened. And now if you go to a coral reef conference, there's 2-3 days of talks about coral bleaching and the mechanisms and so on. And of course, based on what we talked about this morning, these bleaching events are becoming more and more frequent. And this, again, is a few years out of date, but these stars are becoming more and more frequent. Incidentally, bleaching doesn't only affect corals. Here's an anemone that's bleached. Anything with those zooxanthellae can bleach. Soft corals, clams, all sorts of things. But it's corals that get the attention because they're the reef-building organisms. The other interesting thing is when these corals get their zooxanthellae back, sometimes they can get ones back that are more resilient or better adapted to warm waters. There might be a trade-off in that the coral might not grow as fast, but we're going through this big natural experiment of can corals become hardier and better adapted to these high temperatures. So we're getting these repeated bleaching events. Here's that mass coral bleaching event in 1998. So what you're seeing here, I'll run it through a few times. You can see the dates. Starts around June 1998 and runs through. And you can see this pulse of warm water coming through the Caribbean or Caribbean. You figured it out. And these black dots are where bleaching events occurred. And so this was a real wake-up call for coral reef science that these bleaching events there were places like the Seychelles where over 90% of corals on shallow reefs died, and we had a big event here. And notice these are not actual temperatures. These are just 1 or 2, 3 above what they should be normally. So 33 instead of 30 as it should be in the summer, something like that. Now we have the technology to better predict these events. This is a product from NOAA. This is the warning system where they can say, hey, a little bit like a hurricane watch or a hurricane warning, these are places that we predict based on sea surface temperatures might be susceptible to bleaching. And of course, now we can get people in the water and check whether those things are actually happening, which species it's affecting, are the corals recovering or are they dying or so on. So we have these better tools to predict bleaching events. The flip side of that is that we can now make predictions about how often bleaching events might happen. So what you're seeing here is the orange is over 90% chance that on any given year there'll be a level 2 warning. Not necessarily that there'll be bleaching, but there will be a warning. By 2030, which is the top panel, you can see lots of the world's reefs are more and more frequently going to have these annual events. And then by 2050, these events pretty much at least a warning every year. And of course, the worry there is the reef has no time to recover. If you're just being bleached every year, any recovery that happens, and that's going to be slow, take multiple years, and then it just gets bleached the next summer, and so on. So, this is why we need to do something about rising carbon dioxide. And indeed, the evidence on the reef backs it up. This was a headline from I think 2015, 2016 about the Great Barrier Reef for the first time getting bleaching in 2 consecutive years. So what happens after a bleaching event will depend on a bunch of things, but certainly in the Caribbean, it depends on grazers. Do we have enough grazers out there? And what by grazers or herbivores, I'm thinking about things like our friend the parrotfish here or sea urchins that keep the seaweed under control. Because without these lawnmowers of the ocean, if you like, or lawnmowers of the sea, reefs would get overgrown by seaweed. You'd have seaweed reefs instead of coral reefs. And that's the reason why there's no collection of parrotfish in the Florida Keys, is to maintain this function of them keeping seaweed under control. And so whether the reefs will recover will depend on how healthy our grazing community is. Plus, have we still got some adult corals to reproduce and produce larvae? Can we help kickstart that by coral restoration and outplanting corals that you'll hear much more about later? And really, this is all on, these days, a lot of this is on the fish, because back in the 80s, there was a wasting disease, a pathogen that killed most of the long-spine sea urchins in the Caribbean and had a fundamental effect on the ecology of the region. Now it's all on parrotfish, and we need to protect them in order to keep that seaweed under control and at least give reefs a chance to recover. Because after recovery, if it's all covered with this little kind of turf algae, then we're fine. When we get to this stage, we have a problem. That's big green macroalgae. And just to give you some idea of what that looks like, here's a reef that's been pushed too far into that kind of seaweed-dominated state. And you can see all this brown seaweed. There's a little parrotfish desperately wondering, hey, this is more than I can handle. And just to give you an idea of what the problem is, it takes a huge amount of effort to switch a reef back from this state. Look at this little coral just here. Imagine what a tough life it has. It's being overgrown by that seaweed. It's going to struggle to expand and reproduce and do all the things we need to recover. And so when we think of coral reefs, the problem is reefs get stuck in these states. It's great if they're stuck in a coral-dominated state, but if they get stuck in a seaweed-dominated state, it's really hard to push them back the other way. And the reason for that is we just end up setting up kind of feedback loops. So here's the good situation on the left, where we've got lots of fish grazing the seaweed. The seaweed is clear, so we get baby corals settling, which then grow. They provide structure. The fish love structure, so you get more fish, so you get more grazing, so you get more baby corals, you get more adult corals. And basically, the reef just gets better and better and better, and it recovers over time. Whereas on the left, when we get stuck in that kind of seaweed-dominated state, the fish have nowhere to hide from predators, and parrotfish sleep in structure at night. And so they leave, and then you get more seaweed, and then it's harder for corals, which means you get more seaweed, which means fewer fish, and so on. And so that whole process, we're obviously trying to shove reefs back over here to the left, but you can think of it like a teeter-totter, and things like overfishing and nutrients and sediment and disease and some of these other things are just constantly pushing reefs to the right. And so what we want to think about is marine protected areas, marine reserves, coral restoration, some of these other cool technologies you're going to hear about. Can we help kind of shove reefs back to the left and into that stable state that we prefer? The other thing that parrotfish do when they're swimming around a reef is that they're keeping seaweed under control, but they're also eroding the carbonate structure. And so I wanted this to play. I know you just had your lunch, but this is a montage of parrotfish pooping, because what scientists do is we do things like this. We swim around on glorious reefs trying to get in the plume of parrotfish. And so what you're seeing is as they take a bite, they're scraping the carbonate substrate, they're taking all the goodies out of it, and then they're just pumping basically sand out the back. And so if you ever sit on a white, sandy, natural beach, 80 to 90% of the sand you're sitting on is coral reef, is parrotfish poop. So there's a fact to surprise your friends over dinner. So all of these things are interconnected. We lose structure, we lose fish, we lose storm defenses, we lose tourism, we lose our beaches. And so when we look at things like this time sequence from Carrisforth Reef in the Keys, and we see what it used to look like back in the 70s and 80s, and then the same spot in 2014, you can see not only have we lost the coral, but we've lost the structure. And in my lab, we're really interested in the role of structure. Fish love structure. They don't necessarily need live coral. And in fact, what they really look for is structure, whether that's dead coral, live coral, or an artificial reef. They love this structure. And so as we lose those corals and those corals are not recovering, we're losing the structure that supports the fish. And so this is all the sort of things coming together and affecting all those ecosystem services that we get off of reefs. The other thing that's happening, and this is this idea of tropicalization, which is as species have the ability to move further poleward, whether that's north or south, we end up with tropical species in temperate areas. This is a cool sequence of photographs from Japan where you had a kelp forest, and then over time, tropical herbivores showed up, and also kelp don't like warm water. And so we lost kelp. We ended up with kind of bare rock or rocky reefs, and then corals started showing up where previously they might have died during a cold winter. They can kind of survive. So we've switched from a kelp reef to a coral reef. And you could say, well, that's a good thing. I prefer a coral reef compared to a kelp reef. But it's a fundamental, and that might be true, but it's a fundamental change of the ecosystem, as we've been hearing about earlier today. And so that's temperature. This is this idea of acidification. And again, I don't want to turn this into a chemistry lecture, but just be aware that as carbon dioxide increasingly dissolves into water, we end up making the water more acidified. So you probably know that a pH of 7 is about neutral, and 1 is highly acid, and 14 is alkaline. And so the water is not acid, but it's acidified. It's a lower pH than it used to. And again, the problem with acid is it makes it much harder to lay down a limestone skeleton, which we just talked about is something that corals do. So we worry about slower growth, weaker skeletons, and potentially being more susceptible to damage. And to give you an example of what that might look like, this is a natural methane seep that's acidifying the water in, I think it's Papua New Guinea. And so the seep is about here where this red spot is. And you can see those waters are highly acidified. So this is a natural kind of process, but it gives us an idea of what our reefs might look like in the future. So as you go further away, we get back to more natural conditions. So if you go here at A, the reefs look like this, how we want reefs to look: biodiverse, high coral cover, lots of fish. And then as we go to position B, we got slightly more acidified. We've still got corals, but we can see we've got fewer species. We've got the ones that are more tolerant and able to lay down their skeleton in these more acidified waters. And then as we get right on top of those bubbles and those highly acidified waters, this is what the reef looks like. And so this is basically a spatial representation of what we might be doing through time to our coral reefs, just making it harder for them to lay down that skeleton and recover. And on top of that, obviously they might get bleached during the summer when it gets warm. And so, as I mentioned, we don't necessarily think too much about the effects of sea level rise. Fish will deal with swimming. There might be more sea available to them. We think that most of our corals can keep up with rising sea level. This was one interesting example that I worked on when I was in Australia, which is they get these big habitats that we don't really get in the Caribbean. These reef flats, these shallow areas, and at low tide, if you're not a snorkeler, it's a great place to go and have look at a coral reef because it's kind of ankle deep and you can walk out there and you can see some fish. These cool epaulet sharks that have the ability to live at super low tide and basically shut down all of their organs and live in almost oxygen starved states until the tidal water comes back in. So this is what they look like at low tide. And this is what they look like at high tide. You've got sharks coming in and it's 2.5 meters of water and the ecosystem has completely changed. And if you're a prey fish, could be a good news. This is when your predators have to leave because you can stay there because you're small enough, but your predators have to leave. But maybe in the future, instead of your predators having to leave at low tide and then come back at high tide, so you get 6 hours without being chased around and being worried about being eaten, maybe in the future, those predators can stay there all the way through the tidal cycle, which is good for them, but might upset and unbalance the food chain or the food web. And so that's one example of how sea level rise might impact coral reefs. So this is a little summary of what we've talked about. These are all the impacts of climate change. We've got bleaching and sedimentation. Bob talked about the change of the currents, acidification, and so on, and some ideas of things we can do, obviously, to reduce our carbon footprint, which we'll talk about more. And then, again, being a fish person, I wanted to just show you this, and there's way too much information to go through, but just to make the point that whichever level you think about, whether it's at the genetic or the individual fish level or the population or the ecosystem, climate change is having these multifaceted effects, whether it's on the physiology, the growth rate, the genetics, the evolution, the speciation rate. All of these are being impacted by climate change in ways that we don't really understand because being in such a biodiverse ecosystem, it's very hard to think. For example, there's some research that suggests that if you bring up a fish in a high carbon dioxide water, it rewires its brain to a point where not only does it not recognize its predators, but it swims towards them. And there's been some debate about whether that result holds true for that many species, but it's an interesting. That might be good again for the predators, but not so good for the prey. So we're running this massive experiment in a very complex system that's very hard to model and understand, and having all these impacts at all kinds of different levels. And we're only really sort of beginning to figure out what all the impacts are going to be. And the other thing, of course, to remind you is that we've talked about the impacts of climate change. I haven't mentioned sedimentation and pollution and invasive species and overfishing and all these other things that are also layered on top of those climate change impacts. And so here's, for example, coral disease. This is white band disease. Scientists are not super original. A coral gets a white band that's a disease. We call it a white band disease. Fishes with yellow tails, a yellowtail snapper. And you may not know, but while we were going through COVID, corals were deep into a battle with, again, another original name, stony coral tissue loss disease, which originated in Florida and then spread throughout the rest of the Caribbean and has now reached most reefs in most parts. And it's just yet another threat and yet another limitation to the recovery that we're looking for. And so it's kind of timely to have this conference now. You may have seen all the publicity that went with this report from my alma mater in the University of Exeter, Global Tipping Points in 2025, on this idea that as bleaching becomes more frequent and these other impacts become more prevalent, we're at one of these tipping points. And depending on what side of the bed I get up in the morning, maybe we're here, maybe if it's a Monday morning, it's kind of here. But, we are at this critical point that we can decide which of the trajectories we're going to take. Okay, so I've done the depressing stuff. We're very good at taking a reef from the left-hand side of this figure to the right. We know exactly how to do that. We overfish them, we burn fossil fuels, we develop the land, we increase nutrients. The question is, can we do this? And there's multiple ways that we can do that and try and shift these reefs back from this seaweed-dominated state back towards a coral-dominated state. And so marine reserves, and I'm going to talk about them briefly now. You're going to hear much more about coral restoration later, whether that's coral restoration or trying to bring back the urchins and give our parrotfish some help with grazing seaweed, sinking artificial reefs to sort of try and reduce some of the pressures on reefs. There's lots of things that we can do, and I did say that I would try and finish on a positive note. This was some work we did in the Bahamas. So this is the Exuma Keys Land and Sea Park in Exuma in the Bahamas, one of the oldest, biggest, best enforced marine reserves in the Caribbean, and a really good example of what marine reserves can do. Because sure, you stop fishing inside a marine reserve, you will get more fish. That kind of goes without saying. But there are all these other impacts that marine reserves can have. And one of the questions we asked was, okay, well, what about if you're recovering all the grouper and all the snapper and maybe some of the sharks? Isn't that going to feed, aren't they going to feed on your parrotfish and have that negative effect that we talked about? It turns out if you stop fishing, the benefits to parrotfish they're not the brightest fish. They are very susceptible to getting caught in traps. And if you stop fishing, you actually benefit them more than the increased predation has a negative effect on them. Maybe the small ones, you have fewer small parrotfish, but the big ones are the ones that are doing all of the grazing. So as you increase grouper, you actually do get more large parrotfish, which means you get less seaweed, which means you get a noticeably and quantitatively more of these baby corals settling and recruiting, and the coral reef will recover quicker. So marine reserves, just stopping fishing, not the whole reef, just parts of it to allow parts of this reef to recover, can have all these effects on top of these fish spill out into the surrounding areas, and so it can benefit the fishers. Most fish have larvae that float around in the water for a month or two, and those are not necessarily settling back into the marine reserve. They might be settling on fish reefs up to 10, 20, 30 kilometers away, and so they're restocking those reefs. So marine reserves offer us a chance to really address at least some of these local threats. It can't do anything about bleaching. It might help us, those reefs recovering, but whether you're in a marine reserve or not, the water's still going to get warm and those corals potentially could bleach. And so to sort of try and land the plane here and sort of try and bring this all back together, these coral reefs, this is not just a academic biodiversity argument about, oh, well, there's lots of species, we should protect them. This is a very real economic question of coastal protection. What are we going to do if reefs are not protecting us and breaking up 97% of the storm energy that reaches our shores? What happens if we can't go out there prospecting for new chemicals in sponges and soft corals that might be useful medicinally? What happens if we're not catching fish? What happens if tourists go somewhere else because they've heard that reefs are no good in Florida or wherever it might be? And so addressing these questions is super important. And yes, we can't do anything about climate change. Or locally, that's a global problem. But just imagine COP30 is going on in Brazil at the moment. Let's take a moment just to think, maybe they solve climate change while we're sitting here. Maybe we'll all go on the news and they've solved it. If they solve it, we still have the issue of overfishing and disease and sedimentation and pollution. So why don't we at least take care of those now? We can do those locally. And there is lots of evidence that we can buy time for reefs. If reefs are going to get hit by coral bleaching annually by whenever, 2050, maybe if we have plenty of parrotfish and everything else is taken care of, maybe we can push that back to 2075 until we have a real problem. So let's take care of these local threats, which is what we're trying to do in the Florida Keys National Marine Sanctuary and other national parks. Let's take care of those local things, buy these reefs some time until we address these bigger issues like climate change. So with that, I'll finish. Thanks for your attention, and I'll take any questions.
We have one over here.
Thank you. I have a question for you on the marine reserves. How are they enforceable, and who is acting to enforce them, and is it working?
Okay. I'm trying to work out which of my 2-hour undergraduate lecture about marine reserves to give you. So one of the things about coral reefs is lots of people fish for different things. There's lobster and snapper and grouper, And so it's very hard to have that done by quotas unless you have a lot of resources. You can't. It's much easier to just buoy off. Look at me. To just take an area and say you can't fish within that area. It's much more enforceable. It's very obvious. Are you in and you're out? It's not, well, if you're here, you can take grouper, but not this. So marine reserves, particularly in places that don't have the resources like Florida, they don't have FWC. If you're in the Philippines or somewhere with limited enforcement, you can just say, hey, let's just make that. And there's a long indigenous community history of taboo areas and rotating around different reefs that we can build on. And so enforcement is relatively straightforward. It's just you can't fish on that reef. However, you do have to have some level of enforcement. And there's plenty of data to suggest that if you set up a reserve, people think, oh, that must be full of fish. And if there's no enforcement, it's like, oh, I'm going to go there. So you can actually have a bigger impact if you don't have enforcement. So setting up a reserve is great, but there does have to be some budget in order to have wardens or some education materials or some outreach to make sure people understand that. Because but hopefully it can be self-financing. If I gave you the chance, you can dive over there on that crappy degraded reef, or you can pay $10 and you can go to dive in this reserve with all these big fish and corals, you probably pay the $10. So let's use that to pay for wardens and boats and gas and all the other things. So hopefully marine reserves can solve a lot of those issues.
Okay, last question so we can stay on schedule right back there. BK.
Hello, thanks. I was kayaking up in Crystal River, and they were replanting for the manatee. That coral was struggling among the seaweed. Can scuba divers and can we harvest that out of their way? Is that possible? Is it something that happens? Would that help? Thank you.
So I think this is always the issue of, can we do anything on a big enough scale? So it depends. If you mean seaweed, then sure. If it's seagrass, then I would say no, because some of these inland rivers, I know we're losing seagrass. Seagrass is arguably as threatened as coral reefs, and that's food for manatee and green turtle. So don't do the seagrass, but certainly seaweed. And unfortunately, this stuff grows so quickly, especially in a canal with a ton of nutrients. It'll probably be back there within a few days. But sure, if you see a coral struggling under some seaweed, then sure, give it a hand. Right.